This is examples class 10, example 1b. Our first example was to compare the means of two samples. In this example, we're going to determine whether it would be reasonable to assume equal variances. In example 1, we looked at the mean difference and we made an assumption of unequal variances. So now, are we saying this is reasonable to assume unequal variances? Now, in order to make a test of variation, comparing variation, we use an F-test for equal variances. But recall that the F-test for equal variances is not robust to violations of the assumptions, and our assumption for an F-test is the populations are normal distributed populations. So we're looking here to determine whether it was reasonable to assume unequal variances in our first example. So when we're comparing variation, what we're looking at is a test for variances. So our null hypothesis would be that the population variances are equal. Now, of course, here, remember our variance sigma 1 squared for the two populations. So sigma 1 is the standard deviation for those people with tertiary qualifications, and sigma 2 will be the population standard deviation for those workers with no tertiary qualifications. So the null hypothesis for a test for variation is that the population variances are equal variances in the populations. The alternate hypothesis would be that the variances are not equal. So here sigma 1 squared is not equal to sigma 2 squared. And this is, of course, a two-tailed test. So those variances are not equal. Now, using again the alpha value that we had in the first example, 0.01, the F test for variance requires us to have a null hypothesis. Alternate hypothesis is two-tailed, and we need the degrees of freedom for the numerator and denominator. So degrees of freedom for numerator and denominator are determined by our F-test statistic. So what is the F-test statistic? Well, we use the F-test statistic is larger sample variance divided by smaller sample variance. We use this formula, larger sample variance divided by smaller sample variance, because it allows us to just consider the right-hand end of the F distribution. The F distribution, you may recall from lectures, is a non-symmetrical distribution. It starts at 0 because we are determining the variances by dividing one variance by the other. It starts at 0 and it's a right-skewed distribution. If we have larger sample variance divided by smaller sample variance, we only need to consider the right-hand end. And the degrees of freedom for that critical test statistic then will be the degrees of freedom for the larger sample variance divided by the degrees of freedom for the smaller sample variance. Our sample variances for these two samples, the larger variance was 24,000, and that came from the larger sample, which had 50 in it, so that's 24,000 squared was the larger sample variance. 50 minus 1 equals 49, that's the numerator degrees of freedom. And we were dividing by the smaller sample variance, which was 14,000 squared. That smaller sample variance came from the sample with 25 workers with no qualification, so 25 minus 1 equals 24. So, two tricky things to work with here. First one is, how do we find the correct critical value for F? Now, the F critical value depends on numerator and denominator degrees of freedom, as well as the alpha value. So our alpha value here, 0.01, so we are using a two-tailed test, so we need to divide 0.01 by 2. That would be 0.005 at the top right-hand end, and we now need to find the correct critical value. So because it's a two-tailed test, we have to divide alpha by 2 and put half of it at the top end. So the critical value now requires us to have numerator and denominator degrees of freedom. So in Excel, over to Excel, we're going to use the critical value for f, which is the FINV function. And if we go to Excel and look at what required in Excel, it needs the probability, so that is the value of alpha, which is 0.005. It requires degrees of freedom 1, so that's numerator degrees of freedom, which in this case was 49. And it requires the denominator degrees of freedom, which in this case was 24. So 3 figures that need to go in there, and that returns us the critical value of f, which is 2.707. So we're going to write down there 2.71, taking that value to 2 decimal places, 2.71. So our decision in this case would be to reject the null hypothesis if our calculated test statistic is bigger than 2.71, and of course we now need to work out what that is. So over on the right hand side of the screen we can see the test statistic calculation, which we're just about to finish off, and that 24,000 squared divided by 14,000 squared, which comes out to be 2.94. So there, our test statistic, as we can see, 2.94 is in the rejection region. So our decision is reject the null hypothesis. And if we reject the null hypothesis, because 2.94 is bigger than the critical value of 2.71, it means it's over in the rejection region there on the right-hand end. Our conclusion would be we have sufficient evidence to suggest that there is a difference in variation for the two groups, so it would be correct, as we did, to do a test for unequal variances. That would be, in our first example, it was correct to use unequal variances because we have here compared the variation and shown that if we are assuming normal populations, which may be an unreasonable suggestion here, that we have sufficient evidence to indicate there is a difference in the variation for the two groups. And that's the end of that example.